Alright gang, here we go. This is for Physics Unit 8, Part 8. In this video we're going to be talking about interference. Should be a lot of fun. Later we'll talk about diffraction. Alright, so this is almost it. You've almost made it through Unit 8. Proud of you. Keep going. Hit the gas. Alright, so let's take a second here and talk about constructive and destructive interference. Way a long time ago when we talked about sound, we talked about constructive versus destructive interference. And we talked about how if two waves hit each other, right, if one's going like this and the other one's going like this, and when they hit each other, they'd make a really big wave like this, right? And then, or you could have, so this would be constructive interference, or if you had something like this where you had one wave like this and then another wave like this, they'd hit each other and it'd be destructive interference. Okay, and so then these waves can either add up with each other or cancel each other out. All right, so this is essentially what we're doing, and this will occur with any waves. And as we've learned over the last couple weeks together, that light is a wave. It travels as a wave. All right, and so because of that, you can have constructive and destructive interference with light waves as well. Now, in order to visualize that, I want you to take you back to when we first talked about waves or light. Okay, we drew a flashlight that looked something like this, and then I showed you, well, coming out of this flashlight is a bunch of waves, right? That's not my best wave I've ever drawn, but it's all right. Okay, so there's a wave, and then you got another wave, and then you got another wave, right? And then we drew these lines, right? These curvy lines that did something like this. And remember, these curvy lines were called wave fronts. And these wave fronts lined up with the crest of our wave. All right, not my best wave fronts. So anyway, so here's our wave fronts. All right, so if you imagine that you took light here, okay, and you put two light waves together so that they hit each other in constructive interference, what would that look like? Well, constructive interference means it gets bigger. So with light, we see that as intensity. Okay, and so so it would become brighter. So when these two light waves, if they interfere constructively, you see a bright spot. And then if you happen to have two waves that cancel each other out, they have destructive interference, that you would see a dark spot. All right, so if you imagine two waves, all right, coming through, so say you have some sort of setup that goes something like this, okay, and you've got your flashlight here, or a light bulb, all right, so here's your light bulb, right, and then so there's this, okay, and then you've got your filament in there. So there's your light bulb. So anyway, light's coming off this guy, and it's coming off, and these are your wave fronts. When it passes through this hole, okay, Huygens' principle says that this light rays are going to come through, and they're going to do something like this. They're going to fill up this entire gap, right? And this is kind of what they do. And so they're going to do this number here. Oops. All right, and they should be equidistant from one another, right? Oh gosh, you're going to see my great drawing skills. And then the same thing would happen over here. All right. Oh, this is not going well. Okay. And then when they start crossing each other, we'll start to see this interesting pattern appear. Okay. Nope, we won't see it. Okay. So let's take a look at this picture here. So you'll see this interesting pattern. So this is from Veritasium's video, all right, talking about Young's double slit. It's a very good video. Here's the link right there if you want to go watch it. I highly suggest it. It's worth watching. He does a great job explaining what's going on here, and there's some funny people he interviews. All right, so anyway, but what he's got here is he's got these two giant green tennis balls, and he's putting them in a lake, and he's bouncing them up and down. And when these balls go up and down, they create waves, just like they do coming through this thing that I tried to draw a second ago. All right, and so when they hit each other, you can see that we have this constructive and destructive interference going on. All right, and you can see that right here, going along here, we've got a place where our waves cancel each other out. And here, there's a place where these waves cancel each other out. And here, there's a wave that's canceling each other out. And here, there's a place. And so that's where we have destructive interference. In the middle here, we have constructive interference, and this is where these waves are hitting each other and constructively making each other bigger. So here, we've got a peak, bigger crests and troughs. than we would otherwise. And in the middle, we have no crests or troughs. It's completely flat. All right, and so that's essentially exactly what's happening with the light when it passes through double slits. Is you've got kind of an area where, like, if you pass it through two tiny enough slits, you get an area that's like a bright spot right in the middle, and then you've got a dark spot, and then you get another bright spot, and then a dark spot, and then a bright spot, and then a dark spot, etc. And it kind of does that on either end: bright spot, dark spot, bright spot, dark spot. Okay, all the way across. And so you get this thing, and this shows us that light isn't traveling through as a particle. Okay, it's traveling through as a wave, whereas when it comes through, it's getting bent and going through this whole place, and then it's getting constructively and destructively interfering with one another. Okay, and so when this occurs, all right, there's a couple of things that need to happen. First, the light has to be monochromatic. Okay, so mono means one, chromatic means color, so it's one colored. So that means essentially they have one wavelength is what we're after. They all have to have the same wavelength. That's key. All right. So they all have the same wavelength, and because we see wavelength as colors, they all have the same color. All right, and so these light waves can be constructively or destructively interfering with one another. All right, constructively interference gets bigger, destructively gets smaller. And so here they've kind of showed us all these different ways and the resultants that they'll make. All right, now in order for this interference to occur, there's one very, very important thing that has to happen. These waves that are hitting each other need to be in a constant phase relationship. Okay, constant phase relationship. Now, so what this means, hopefully when you took trigonometry or pre-calc, you learned about how to graph sine waves, right? And one of the things that you learned about sine waves, you learned about the amplitude, you learned about frequency, and then you also learned about phase shifts. Okay, now phase shifts is how much. So if we were just going to draw, and ignore all this for a second, if we were going to draw a sine wave, it would look something like this. You know, at 0, it's at 0, and then at 90 degrees, it's at 1, and then at 180, it's at 0 again, and then at back the other side, it would be 270, it'd be at -1, and then we'd be at 0, right? And so we'd have this sine wave that goes something like this, right? All curvy like, right? Something like that. And so you'd get the sine wave. All right, and so you learned about how we can make the amplitude get bigger and smaller. You learned about how you can squeeze these guys closer together. But then the other thing you learned is how we could actually just straight up shift this thing one way or the other, and we call that a phase shift. So, and we're doing the same thing because this is a wave, and this is how the electromagnetic waves travel. We're just shifting this guy to the right or left, okay? And so what we need in order for this interference to occur is that our phases need to be constant. We need to be in a constant phase relationship, or that they need to be exactly the same. All right, and so the crests and troughs need to always line up in the same relation to one another, whether they be right on top of each other or completely canceling each other out or somewhere in the middle. All right, so A here, this would be completely in phase. Notice that the troughs line up with the troughs and the crests with the crests, troughs, crests, troughs. Okay, and then B here, all right, B is completely out of phase. The crests are lined up with the troughs and the troughs with the crests. Okay, so if we were going to draw this guy, would be the case where it would get really, really big, and this one would be completely flat. All right, if the waves are in constant phase relationship, we call these coherent waves. All right, these waves are coherent. We create coherent waves in several different ways. Specifically, an easy way to do this is with a laser pointer. Laser pointers remit light at a specific wavelength, and they are automatically coherent. Most light waves, like the light coming out of my ceiling light right now, is incoherent. Okay, it's all out of phase with one another. Some of them are, if we were going to draw it, some of them would be like, so this is a little box of our waves. Some of them would be like this. Some of them would be like, this. Okay, some of them would be, somewhere in between, and some of them would be like this, and some of them would be slightly off center. So they're out of phase with one another. They're incoherent. Okay, so we cannot see interference while using incoherent light. So one of the things that we need to do in order to make sure we have monochromatic light is either use a laser pointer, so we only get one light, or we can use this double slit thing that we were just talking about earlier. And what this will do is allow only the one wavelength in, and because only the one wavelength is coming in, it will automatically be coherent. All right. So in order to demonstrate this interference, we're going to use these slits, all right? And we establish two really tiny holes. Okay, and so a light from one source, and it can be polychromatic, but if we make them small enough, then it doesn't matter. Okay, and it'll create two coherent sources. Then these waves are going to spread out, and we can imagine drawing these wave fronts, and it would look something like this. And these waves don't just travel in one way, they travel all over the place, right? As soon as they come through this hole, it's going to light up this whole room, or this whole area on the other side. All right, so these two waves are going to spread out to take up this whole area, and that's Huygens principle that says that. All right, and now if we establish a screen over here somewhere where these two hit, if they hit each other constructively, meaning the crests hit each other, then we'll get a bright spot. If they hit each other where they cancel each other out, then we'll get a dark spot. All right, we call that destructive interference. Constructive interference is also known as a maxima. Okay, maxima, and then destructive is known as a minima. All right. So, constructive interference occurs when your waves that are coming in, your two distinct waves, come in arriving in phase. So right here, notice that they're both hitting in phase with one another. And so we're going to get a bright spot right here. Okay, and so you've got this spot here where both these waves are in phase, so you're going to get double crests or double troughs, and so you get a bright spot right here. All right, so this would occur. Now remember, it's monochromatic, so that means they have the same wavelength, and then they're coming in and they happen to be traveling the exact same distance. And because they're traveling the exact same distance and their wavelengths are the same, they have to be in phase when they reach whatever spot they're talking about, because they traveled the same distance and their wavelength is the same. So they're going to be at the same point in their crest trough cycle. So they're going to hit in phase. All right, so you're going to have constructive interference. Okay. And then therefore you're going to get a bright spot right there. Now you could imagine, well, when would the next place we get a bright spot? Okay, well, the next place we would get a bright spot is when we're exactly in phase again. And this would occur when when one wave has traveled exactly one wavelength farther than the other. Okay, and so here, this was where the center was, so this was the bright, okay, and we'd have the next bright area here when the wavelength traveled is exactly one more than the other, okay, because this is when we'd be in phase again. All right, in between these two, okay, we would have the dark spot. And so this would occur when our wavelength is exactly half of what it was. Okay, so essentially what we end up with is this, we get this wavelength, and so every single time our wave travels one wavelength farther, okay, we get another bright spot. And so we can use this to kind of figure out an idea of when our wavelength gets, what our wavelength was, all right? Okay, and so our wavelength would occur at L2 plus 2 theta, and L2 plus 3 theta, etc., etc. All right. Now the destructive interference occurs exactly halfway between those, so it would occur at the half wavelength. All right, so here we've got destructive interference, so our L3 plus half wavelength, right? And notice that because they have the same wavelength, this one traveled half a wave farther. So if this one traveled L3 and ended on a crest, and this one traveled half a length farther, it would have to have ended on a trough. And because of that, you'll get destructive interference. They'll cancel each other out. You'll get a dark spot. All right, because they arrive completely out of phase. And in between the two, between the bright spot and the dark spot and the bright spot, you'd have, this transition from bright to dark, 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 and then dark to bright, bright, bright. Okay, all right. You can type these in your and they kind of go through exactly what we've talked about here. All right, now we can use this idea, okay, between all of this stuff, and I'm not going to derive this for you here, okay, but essentially what we can do is we can create a triangle, okay, and we can use this distance here, okay, and the theta of our angle in order to develop this reaction, or this equation here. All right, the equation for constructive interference. All right, so what we're saying is the distance between, the d is the distance between the slits, times the sine theta, and this would be the angle between the slits, is equal to our m value, and this is the order of our maximum and minimums. Okay, so if we're at the center, we say that's order of 0. If we're at the next one, we're at order 1, and then 2, then 3. All right. So this is simply an integer, and it's always a whole number, and then this is the wavelength. Destructive interference, very, very similar to the same thing, except for because it occurs at every half wavelength, we say it's m plus 1/2, and this just times the wavelength. All right, M is the number assigned to the inner first fringe with respect to the central bright fringe, and this is the order number. All right, so let's do a couple practice problems here. Not too bad. It says the distance between two slits is 0.005 millimeters. Find the angles of the 0th, 1st, 2nd, and 3rd order bright fringes of the interference produced by a light with a wavelength of 550 nanometers. All right, so we know, and it says it asks for bright fringes, so we're going to have maximum, right? So d sine theta is equal to m times lambda. All right. So we're solving for theta, so that means theta would be equal to the inverse sine of m times lambda over d. All right. Now, m is what's going to change as we go from 0 to 1st to 2nd to 3rd. Okay. Lambda and d are always going to be the same, so we can just go ahead and solve for what lambda and d would be. All right. So lambda over d, well, this would be equal to 550 nanometers. 550 nanometers. Okay. Over our distance, which would be 0.0050 millimeters. But we have a problem here, right? Because one's in nanometers and the other one's in millimeters, so we got to convert these things. So that means our top becomes 5.5 times 10 to the minus 7th, and then the bottom here becomes 5.0 times 10 to the minus 6th. Okay, so we have 5.5 e to the minus 7th divided by 5 e to the minus 6th, okay, and we get 0.11. All right, so this would be 0.11, so we can plug this guy in here. So this would be sine inverse, okay, of m times 0.11 in all cases, and we can just plug in our different things. So sine of theta of 0, well, that would be, theta order 0 would be sine inverse of 0 times 0.11. Okay, and that's pretty easy. Times 0.1. I don't know why I did that. Times 0.11. And so 0, sine of 0, inverse sine of 0, well, that's just 0. So this occurs at 0 angle. So theta 1, at order 1, would be inverse sine of 1 times 0.11. All right, and so this, we plug this into our calculator. Make sure you're in radian, or you're not in radians, that you are in degrees, because we're talking about degrees, and you should get like 6.29 or something like that. So you get 6.3 degrees, and you can kind of see how this is going. It's just the same idea, different story. All right, so 2 times 0.11. All right, and you should get something close to 13. The last one should get you something close to 19. One more here. It says when monochromatic light falls on two slits with a separation of 0.010 millimeters, the 0th order dark fringes are observed at 2-degree angle. Find the wavelength. All right, so we're finding wavelength, and it says dark fringes. So for dark fringes, our formula is d sine theta is equal to m plus 1/2 times lambda. All right, and we're finding wavelength, so that means wavelength is equal to d sine theta over m plus 1/2. All right. So in order to do this, then all we have to do is plug these guys in. So our lambda, well, our lambda is equal to our d value, and d is 0.010 millimeters, so that would be 1.0 times 10 to the minus 5th meters. All right. And then sine theta would be sine of 2 degrees, right? And that's just this guy right here. And then divided by m plus 1/2. Well, we're at the 0th order dark fringe, so that means our m is 0, so it would be 0 plus 1/2. You plug that into your calculator, and you should get something like 6.998 times 10 to the minus 7th. So with 2 sig figs from this guy here and this guy here, we'd get 7.0 times 10 to the minus 7th meters, or like 700 nanometers. All right, and so that's it for our first little bit. Next video, we'll talk about diffraction. All right, so do practice problems. Let me know if you have any questions, and I'll see you on the flip side.